Inferring relations between variables is the bread and butter of empirical science. Whether it is about the role of asteroidal impacts in mass extinction events, the paleoclimatic interaction between atmospheric temperatures and CO2, effects of keystone species on ecosystem functioning, potential health benefits of a vegetarian diet, or of medical treatments, deducing the existence of Planet 9 based on orbits of trans-Neptunian objects, moving traffic congestion through highway expansion, or the relevance of education for economic well-being. Discerning between effects and their potential causes is a recurring problem across scientific disciplines. Usually this is done with conventional correlation metrics that indicate how strong a supposed dependent variable changes in relation to an independent one. However, depending on the complexity of the investigated subject, it might be unclear to researchers and readers alike which variable in a correlative analysis really is dependent or independent, which other systems might be involved, which additional relations might exist, and what the causal implications are. Does B really follow from A? Or perhaps is there an inverted relation from B to A? What mutual influence does the external environment have on the observed systems? And what internal dynamics might be of relevance to explain the measured data? This video and a related article introduces a new concept that aims to work towards improving transparency, rigor, and reproducibility in contemporary science, the causality coefficient. Being more a framework than a simple index, the causality coefficient is an attempt to structure, guide, and standardize conventional empirical research by expanding it into the realm of causal inference. Its basis is the concept of causal networks, such as the one depicted here, with systems of interest, here A and B, the external environment O, and all possible mutual directed relations between and within systems. Causal networks constitute a universal representation of potential interactions between all kinds of observable systems. As will be evident, approaching statistical inference through the lens of causal networks opens up a relational richness, even for a limited number of systems, a richness that conventional research practices should no longer miss out on, and that the causality coefficient concept presented here will help to explore, represent, and quantify. Depending on the subject under investigation, not all of the relations might be equally relevant. Perhaps some are even non-existent and can be disregarded. However, usually this choice involves uncertainty. So when one considers the basic causal network with 3 systems and 9 different directed relations, one may ask a simple question: how many choices are there? The answer is quite a few. What you can see here are all 512 unique networks that include anything from 0 to 9 relations, sorted in columns from left to right. In a way, this overview can be regarded as a representation of the discrete causal space of alternative, binary causal constellations in which any simple correlation between 2 systems is embedded, when accounting for internal and external influences. When one postulates that there is a particular relation between the involved systems, the space of alternative causal networks gets restricted. For instance, the statement that A causes B excludes half, that is 256 of the 512 alternative networks, with the remaining half being in some variation compatible. With only 2 more defined relations, the selection of dichotomous networks can be again reduced considerably by a quarter to 64 compatible alternatives. With those little demonstrations in mind, it is nothing but natural to attempt to quantify how an initially defined set of relations restricts the causal space of alternative compatible causal constellations, and to assess how closely the systems of interest are related. This is exactly what the causality coefficient aims to achieve, and its principal idea is quite simple. Starting from a set of initial, empirically derived relations between the focal systems A and B, generate all possible compatible networks that can contain the original relations and optionally any other relation. Quantify this implied redundancy of non-excluded networks, then calculate for each of those representative main alternatives their overall causal network power, which measures how strongly the focal systems are directly or indirectly related, in both directions, from A to B and B to A. And finally, combine both the network redundancy and an aggregate of all causal powers of all alternative compatible networks into a combined uncertainty and causal strength metric, the proposed causality coefficient C. Before detailing how this coefficient is calculated, it might be useful to clarify how each of the presented causal network components are supposed to fit into an analytical context. The nodes of a network are meant to represent the analyzed systems, with their expressed and measured properties. Systems are not defined comprehensively in every aspect. Rather, they are distinguished by a selection of unique characteristics, in other words, by what they are not. Systems are part of a system hierarchy. Each system is itself a hierarchical aggregate of internal subsystems. Likewise, a collection of interacting systems can itself be thought of as forming a common supersystem. This fractal hierarchy approach principally allows to expand the simple three-system networks in this overview to include an arbitrary number of systems and relations. However, such a generalization is beyond the scope of this introduction. Additionally, for practical applications, a common system definition nomenclature should be used to avoid redundancies and overlaps. Such a nomenclature is also beyond the scope of this overview. The directed relations between systems are meant to represent causal interactions between exposed properties of the involved systems. Relations fall into two groups. Firstly, automorphisms, which are relations where origin and target is identical. And secondly, allomorphisms, a neologism, which target a different system than the one they originate from. To quantify the strength of a causal interaction between systems, each relation has an assigned causal power ranging from 0 to 1, where 1 indicates full causation between two systems. Causal power is distinct from usual correlation metrics. In essence, it can be thought of as a causally directed form of correlation, and should not be confused with negative or positive correlation, which do not imply a specific causal direction. A general outline of how to derive causal power by inferring the causal direction of a correlation is shown at the end of this video. The external outward and upward part of the system hierarchy is represented by the external environment node O. It is connected via all possible bidirectional allomorphic relations to all other systems of interest on the current hierarchy level. In contrast, the internal inward and downward portions of a system's hierarchy are represented by a system's automorphism. Automorphisms are meant to represent the causally irrelevant parts of the variation of a system. As such, they are not relevant for the transmission of cause and effect between different systems. In order to compare the causal power of different causal networks with each other, they first have to meet some common criteria, which are summarized under the term network completeness. Given a set of focal systems, here A and B, a network is considered complete when: first, it contains a node representing the external environment O. Second, all systems have an automorphism assigned. Third, all allomorphic relations between systems are defined. Fourth, the causal power of each relation has been specified and is non-redundant, that is, it does not overlap with any other ingoing relation of the same node. And fifth, the sum of the causal powers of all ingoing relations for each node adds up to exactly 1, as can be seen here for A, for B, and for O. As long as the sum of ingoing relations is equal to 1, relations can have any power between 0 and 1. By convention, if a relation has a causal power of 0, it can be omitted from the graphical representation. This reduced network is identical to the previous one, and it is likewise considered to be complete. Having established a common standard to compare the causal powers of different causal networks, this can now be used to assess and quantify the overall causal power of a set of compatible networks that we have seen before. The first step for this is network completion. That is the extension of a set of initially given relations to match those of a particular compatible network alternative. For instance, given any incomplete network with the three systems A, B, O, and the relations AB, BA, and BB with their respective causal powers, it can be extended with the relations AA and OA to form a new alternative compatible network. How should the relations be adjusted to maintain the original implied causality on the one hand, but also allow to test the causal significance of the added relations on the other? Well, for each node the ingoing relational power needs to add up to 1. In case of A, there is one ingoing relation initially given, BA with a power of 0.3. Thus, the remainder for A is 0.7, and it is divided equally between all unquantified ingoing relations AA and OA. For B, there are two relations given, AB and BB, with a combined relational power of 0.6. Since there is no alternative unquantified relation specified, the power remainder of 0.4 is simply added to B's automorphism. This leaves the node O, which has no ingoing relations, neither allomorphic nor automorphic, and therefore a power remainder of 1. In case a node has a power remainder, but no unquantified relation, the relation restriction is overruled, and the remainder is assigned, as in the case of B, to the node's automorphism. To summarize, a network is completed to match a set target network by first calculating the non-redundant relational power remainder for each node, and then by distributing this remainder equally between all complementary relational powers if available, or by adding it to the node's automorphism. This maintains the original causally relevant relations, while producing a representative complementary network with balanced relational powers that can subsequently be evaluated in terms of its overall causal implications. To assess the overall causal power of a complete network, all relevant paths that transmit causality need to be evaluated. In case of the simple networks with three systems, there are effectively two options. A can affect B directly or indirectly, by first influencing some external system in O, which then in turn interacts with B. And of course, causality could also be inverted, with B causing variation in A directly or indirectly via O. So how can the causal power of those direct and indirect, inverted and non-inverted causal paths be quantified? To resolve this, in the next step, a rule needs to be defined how to calculate the overall causal power of a path of successive relations. For networks in this overview, this only comprises indirect causality paths via the external environment O, as seen in this example. While various options exist to combine successive relational powers, here they are simply treated as multiplicative. That is, the overall causal power of a path connecting two systems is equal to the product of the involved relational powers. This means that the final ingoing relational power is also the maximum causal power that a path can have, which in this example is the relation OB with a power of 0.2. The overall causal power of this particular path example is therefore 0.1. Of course, two systems can be connected through multiple paths. So how should the causal power of those alternative paths be combined in turn? Here the fact that we are dealing with a basic causal network helps a lot, since there are only two alternative paths from A to B, which do not share any common relations and are therefore exclusive. Since all final ingoing relations of a target node are non-redundant and therefore additive up to a total of 1, so are the unique causal paths they are associated with. The combined total causal power of all causal paths between the systems A and B is therefore in this simple case the sum of the individual alternative path powers. In this example, this means that A affects B with a combined direct and indirect causal power of 0.6. For networks with more than 3 systems, this simple rule would have to be altered, since now paths could overlap or pivot back to an already visited system. However, for this overview, the simpler additivity approach suffices. With a procedure to complete a causal network from a set of initial relations and rules to handle successive relations and alternative causal paths, we can now calculate the overall causal power of a network. Given a network with all causally relevant allomorphic relations and their relational powers, the succession and combination rules can now be used to calculate the overall causal effect of A on B. Here 0.5, since the indirect effect is 0, and of the inverted influence of B on A, with a combined total of 0.44. The overall causal power of a causal network phi is now simply equal to that of the dominant causal direction between A and B, where the overall causal power from A to B is defined to be positive, and the causal power from B to A to be negative. This is achieved through the symmetric maximum, which returns the signed value with the largest absolute distance to 0. Thus, this example network has an overall causal power phi of 0.5. The last remaining piece is to create an index for causal network redundancy, which is also straightforward. Given a selection of initial relations and their associated compatible networks, the network redundancy is defined as the ratio of all compatible networks minus the reference network divided by the total number of networks minus the reference network. Therefore, if all relations have been specified, the index has a value of 0, and with no specified relations, the network redundancy is 1. To get a more conservative value, the subtrahend 1 can be substituted by the causal network power phi of the reference network. This makes a marginal difference when not many networks are excluded, but has a larger impact the fewer compatible networks exist. For 256 networks compatible with the relation AB at a presumed causal power of 1, the network redundancy is about 0.5. With this, all components are in place to be assembled into the causality coefficient. Based on an initial, potentially incomplete set of relations, one can now generate all compatible networks that include those relations, then complete each of those compatible networks by attributing their unquantified relational powers, followed by calculating the overall causal power for each compatible network, and finally combining this into the causality coefficient. It is defined as the median of the causal powers of all completed compatible networks multiplied by the difference of 1 and the network redundancy. Similar to the causal network power, the causality coefficient ranges from -1, full inverted causality from B to A, to 1, full causality from A to B, with 0 indicating no causality between the two focal systems. Since the median causal network power is scaled by the network redundancy, the maximum median causal power of 1 or -1 is not sufficient to achieve the maximum coefficient value, if not all other alternative compatible networks are excluded by the initially inferred relations. To get a better feel how the causality coefficient scores different causal networks and how it is mapping out causal network space representative of the major alternative causal constellations to the initially given relations, let's look at some examples. Assuming full relational powers, if not otherwise specified, in case of direct and inverted direct causality, the causality coefficient results in an intermediate score of 0.5 and -0.5 respectively. For indirect causality and its inverted counterpart, the score increases substantially to about ±0.75, since now 2 instead of 1 relation are specified, which shrinks the amount of compatible networks. Similarly, for direct feedback with A affecting B and vice versa, the score is 0.75 as well. The value is positive, since in case of ties, causal network power is also positive. In contrast, an indirect feedback between A and B via O has a much lower score of 0.49, although now 4 total relations are given, reducing the compatible network count to only 32. This is because O has in this case 2 ingoing relations with a power of 0.5 and not 1, to allow for equal causal transmission in both directions. Since all relations have full power, this is not the case for a semi-direct feedback and its inverted version with 3 relations. Both reach therefore the highest causal score in this example of 0.88. In case of what one can call a correlation between A and B, that is an external forcing on A and B via O, the causality coefficient takes a low score of 0.15, notably not 0, since this correlation pattern still allows for some compatible networks where A and B affect each other. Lastly, the variation in A and B could be completely coincidental, that is caused by internal dynamics in both systems. This excludes any causal transmission between A and B, therefore the resulting causality coefficient is 0. Overall, the causality coefficient gives satisfying estimates that resemble the general causal connection between the involved systems, but also clearly rewards a thorough causal analysis, where as many relations as possible are initially inferred and quantified. To conclude this overview, this last section briefly covers how the causality coefficient could be incorporated into an empirical analysis, specifically how a causal network can be inferred and quantified in the first place. The following remarks are only a general illustration that intends to show that such a bridging can be done in principle. They are not meant as a concrete analytical template, since many of the involved steps still have to be combined into a coherent statistical procedure. Nevertheless, as before, suppose one would like to assess how some systems A and B are causally related. One would start with measuring the system properties of interest, creating a time series dataset for each system. Ideally, those system measurements should be conducted under conditions where all systems are exposed to each other, and under conditions where systems are isolated or separated. Such a combination is invaluable to infer the causal direction of effects between systems. Assuming such time series datasets under exposure and isolation have been produced, one can then continue the analysis by fitting functions to all measured time series via various regression methods. In the next step, those fitted time series functions can then be decomposed into fundamental component functions for each time series, in this example 2 for each system. The general idea now is to correlate and compare each of the fundamental component functions of one system separately and in every combination with every combination of component functions of the other system, to find the combination of components that produce the best correlation and thus show a relation. However, since cause and effect might not be immediate, the involved time series usually have a relative time lag to each other. If one does not account for such a lag, the resulting time series correlation does not produce an optimal fit, as can be seen for the correlation of the combined components of both systems. Therefore, this time lag first has to be removed by shifting the time series against each other. If B is shifted somewhat to the left, one can eventually produce a perfect positive correlation, where both time series overlap perfectly. If this were the real-world time lag, this would mean that the variation in B is caused by A. This, however, is not the only option. If B is shifted to the right, a strong negative correlation can be achieved, where an increase in B results in corresponding decrease in A, which implies a reverse causal direction. In order to decide which combination of components produce the best correlation, and therefore might be causally related, all combinations of components of all systems have to be cross-shift correlated with each other, where generally the strongest correlations with the least amount of shift should be preferred. As with the basic time series measurements, this should be done under combined and isolated conditions. If two systems only display a certain variation and therefore correlation under combined conditions, but no variation when isolated, one can conclude that the variation in both systems has a common cause. If one system still displays a certain variation under isolation and the other does not, this clearly indicates a causally directed correlation. Alternatively, the shifted direction that produces the best correlation can be used as a preliminary indication of causal direction. This, however, cannot substitute isolation measurements. When a relation and its direction has been established one way or another, one can then quantify its causal power. Various options exist, but an idea is to scale the overall statistical variance in the target system by a measure of correlative strength of the best shifted fit that can be produced, for instance using the coefficient of determination r², which can take values between 0 and 1, with 1 indicating a perfect correlation. Again, both kinds of correlation, positive or negative, are causally valid possibilities here. In this example, this would indicate that all of the variation in B is produced by A. If there is a significant power remainder, an attempt should also be made to attribute it among the remaining relations for each node, which in case of B involves to differentiate between internal and external inferences. Here again, isolation can help. However, a meaningful differentiation might only be possible if O again is explicitly split into concrete external systems, which can be separately analyzed. Thus, this depends highly on the analysis in question. This is also true for A. Again, isolation measurements are key, since causation in one direction does not exclude causation in the other, with a possible feedback relation. The most difficult relations to quantify are relations affecting the external environment O. If O cannot be split effectively into measurable subsystems, such a quantification might be infeasible. The benefit, however, is that the causality coefficient accounts for the comprehensiveness of such a causal analysis, and together with the corresponding graph it becomes easily evident what relations have been established and which are still open for debate. Here are some final remarks to conclude this video. The overall idea of the causality coefficient is to provide a standardized formalization and causal contextualization of scientific inference. Does it meet these goals? At the current stage, important aspects for a full integration into practical scientific research are missing. This mostly involves the statistical operationalization, but also more conceptual aspects, such as a generalization to networks with more than 3 systems, or a common system nomenclature standard. Nevertheless, implementing this framework, even in its current limited form, can still increase transparency by providing missing causal context and improved standardization and documentation, compared to conventional empirical research workflows. This is possible since the coefficient can incorporate and reflect preliminary and definite information. Most of those benefits are intrinsic, however some publication practices might have to be changed. In particular, any empirical scientific publication should include an overview of all research questions that were addressed, an overview of all analyzed systems and their measured properties, an overview of all tested hypotheses about causal relations between systems, a causal summary graph depicting the inferred causal relations and their causal powers, and the causality coefficient or a similar metric that quantifies the overall inferred causality between the systems of interest. Nothing in this framework is particularly complex, original, new, or revolutionary. Likewise, it is far from the only conceivable or even viable approach that could be taken. Whether through this framework or similar approaches, it is my hope that this call for a causal invigoration of conventional research does not go unheard, since it has the potential to greatly improve the quality of conducted research. If I have sparked your interest and you want to know some more details about this framework, perhaps to apply it to your own projects or to contribute, expand, and improve it, I invite you to read the accompanying article that is linked in the description. Also, feel free to share it and this video if you want to spread the word. Thank you for your time and attentiveness. Be well and, perhaps, Let's revolutionize science.